We're at the end of the semester, and this is where the slides fall apart too, because I always run out of time at the end of the semester and I don't fix the slides. And it's like every semester. So, anyway, section 17.7, the Chatelier's principle. So we talked about what an equilibrium was, and now we're going to look at what happens with changes in an equilibrium. So if we have a change of concentration for an equilibrium reaction, remember an equilibrium is where we have a forward reaction and a reverse reaction. They are happening at the same time. So the concentration of reactants overall isn't changing. The concentration of products isn't changing anymore, and yet there's activity. If we look on the particulate level at what the molecules and atoms are doing, there's a lot going on. If we look at it with our eyes, it looks like nothing's happening. So what happens if you add a reactant or add a product to that system? The system is going to shift away from that. Another way to think of it is that the equilibrium fights back. Whatever you do to it, it's going to try to undo. Okay, so it's like a person who just likes things the way they are. And you try to, upset things, and they're like, no, we're going to make it the way it was. We just want to keep everything the same. So if you add a reactant or product, the system shifts away from that. If you take away reactant or product, the system's going to fight back, and it's going to shift in a way that will replace the product that you removed. So here's an example. It's really small. So here we have an equilibrium between nitrogen gas and hydrogen gas and ammonia gas. If we add nitrogen to this, the reaction is going to shift in a way to get rid of that. There's no chemical equation on here. We need a chemical equation. We need to see the equilibrium. So I'm going to, where should I write it? Maybe I can stick it in over here. So we've got H2 plus N2 in equilibrium with NH3. There's going to be 2 of those and 3 of these. So there's an equilibrium. We've got hydrogen, we've got nitrogen, we've got ammonia. The reactions are going in both directions at the same time, and all the concentrations are remaining the same. Now, if we add nitrogen, the equilibrium wants to fight back. It's going to shift either to the right or to the left to undo what was done to it. So we added nitrogen. So if it shifts to the right, that's going to cause the concentration of nitrogen to go down, isn't it? So when we add, the equilibrium shifts to the right, shifts away from adding. If we were to add ammonia, it would shift that way. Does that make sense?
Say that again?
Yeah, I didn't see anything change in the equation.
I've learned how to get that back. The equation stays the same, but the concentrations change. And we'll talk about this in very general terms. Okay, so in the other...
Concentration changes.
The concentration of the substances will change. So you're adding nitrogen. Okay, so let's go to this analogy that they use in this other book. So you have... Actually, I better draw a picture. It'll be beautiful. Why do you do that? Okay, I'm just going to get rid of that. Okay, so here we have, this is a country. And there's this river that runs through it. And this side is Narnia. And this side is Middle Earth. This is from the 3A book. So initially, let's say there's a whole bunch of people in Narnia, Now they need to have arms, or they can't farm. So, this represents like thousands of people or something. So a bunch of people in Narnia, and only a few people in Middle-earth. Well, some of the people from Narnia are going to move over here because there's more space. Here it's getting kind of crowded in Narnia. It's hard to get farmland. But hey, if we go across the river to Middle-earth, there's plenty of space. So you get this shifting. And eventually, you get people moving. Whoops. You get people moving in both directions. Okay, so, in the country, if you disregard births and deaths, you've got population shifting around, but overall, the number of people is going to stay the same. But they're not all always living in the same places. So you got people moving to Reedley from Parlier, and you've got people moving to Parlier from Reedley. I don't know.
So how does it add?
Okay, so we've got this equilibrium, and what happens if now we add a whole bunch of people to Narnia? Now all of a sudden we double the population over here. What's that going to do?
Make it crowded again.
It's going to make it crowded, and that's going to increase the rate of people going to the other side. So it's going to cause it to shift over here in an effort to reduce what was done. Does that make sense?
Yeah. In that.
And that. It's the same idea with the atoms.
So it's based on space?
Well, no, it's not based on space. So, did we talk about collision theory in reactions? About how things have to collide, right? So in order for a reaction to occur, things have to collide. And that was helped us to understand that when the concentration of the reactants increases, the rate of the forward reaction increases, right? So in the nitrogen, hydrogen, ammonia thing, let's just do that. Okay, so not with the eraser. The eraser just doesn't make a good pen.
No, I get the principle of it going to an equilibrium. I get that. That
Okay,
part I understand.
yeah,
But
but
what
now-
I don't understand is how the formula doesn't change,
Okay,
even though you're adding something else in.
well, why would the formula change?
I don't know.
The same reaction is occurring. But when we increase the concentration of nitrogen, that increases the rate of the forward reaction. Does that make sense?
Because it moves it away.
Because you've got more nitrogen, so there's going to be more collisions now. The rate of the reaction will increase. This is the more sophisticated.
And it wouldn't matter if you added the hydrogen or the nitrogen.
Right. If you added hydrogen instead, it would also increase. If you added both of them, the forward rate would increase. And we're not talking about how much, we're just talking about increase or decrease or stay the same. So if you add reactant, the forward reaction goes faster.
So if you added the ammonia, it would reverse it.
Mm-hmm.
That's where you're talking about it either would, no,
Yeah.
on the nitrogen.
No, I see it. That's
either
not the part.
add
I'm
it-
not confused on that part. I get that part.
If you added the nitrogen.
I understand you add more nitrogen, it's going to try to shift towards the
Right.
ammonia. But I guess I just don't see how that represents.
It doesn't show in the chemical equation. It doesn't.
It shows in the concentration.
Yeah, you only see it in the
So the
concentrations.
concentration is changing.
The concentrations are going to be different if, you have one reaction flask and another reaction flask. The concentrations are going to be different. But you can affect how the reaction, how far it goes in one direction or the other by messing around with the concentrations of the reactants and products.
Do they then break apart when they go back the other way?
So it's not saying you end up with more.
Yeah,
You do, right?
You do end up with more.
More
So
ammonia.
same idea.
So-
If you were to add a bunch of ammonia, it'd go the other way.
Because whether you added nitrogen or whether you added hydrogen, if you added a single one of those components, you would get more ammonium, right?
Mm-hmm.
No matter which one it was.
Right,
And
so
you added
if
both-
I increase the concentration of nitrogen, that causes the equilibrium to shift to the right and causes an increase in the concentration of the ammonia, and it causes a somewhat of a decrease in the concentration of the hydrogen.
But it eventually balances out once they keep going back.
But it will establish a new equilibrium, but the concentrations on each side are different than they were before. If I take away nitrogen, the equilibrium will shift to the left to try to counteract that. That's, this personifying is what most students understand more than changing rates of reaction. It's fighting back. It's, oh, you're taking away my nitrogen? Well, I'm going to make more and show you. So it shifts to the left, which will compensate for that loss in nitrogen, and then it will cause the amount of hydrogen to go up and the amount of ammonia to go down.
Which part's shifting? The
The balance is shifting.
And those arrows, the way they depicted, that stays the same true. So if I add more ammonium,
Yeah, if you add...
nitrogen goes up, but hydrogen goes down?
No. I should probably use different colors here. So that's not a different color.
If I added ammonium,
This
nitrogen
is
doesn't go
what
up.
I'm doing.
in concentration, in the amount
So the yellow is what I am doing to it, and the black is what happens as a result of that.
No,
If I increase this, it will shift to the left, and both of these will go up.
in regards to the concentration level.
In regards to concentration.
That's what
Not
I thought.
necessarily
adding the ammonia,
that they're
what it
breaking
does is
apart and
produce
doing
more
something at the
reactants.
moment, just that you
You're
have
adding
more
product, it's
concentration.
going to produce both the reactants.
Well, in
And
this
then it will start equaling out.
in this third
Whereas if you add
in this
one
third
reactant,
situation,
it's
by
gonna
adding
react with
more
the other
of the
reactant,
product,
produce more product.
But it's not.
I'm gonna-
But it's so it's breaking it down.
This happened to
So
me
it's
earlier.
actually tearing it apart.
It's producing what it was.
we'll go with green for a while. So if I add more product, then that's going to cause an increase in the reverse reaction. And yes, the ammonia will be coming apart and forming nitrogen and hydrogen
On the reverse.
on the reverse reaction. So I'm talking about this third line here. If I add ammonia, that will cause a shift in the equilibrium. And you can kind of think of it as, like a teeter-totter or a balance thing. And someone pushes you to the right, what do? To stay upright, you have to shift left, right? Because if you have to shift left, right? You have to shift to the left, because otherwise you're going to fall over. If you just keep leaning over, you're going to fall over. So it's a balance thing.
So again, if you added hydrogen, it's going to shift left.
Yes. So if I add hydrogen,
If you take it away, it's going to shift left.
yes. If I add hydrogen, it's going to shift to the right because that will cause a reduction. It will oppose what I just did to it. And the result of that will be that the ammonia concentration will go up and the nitrogen will go down.
If you were to add your reactants and your product at the same rate, like same ratio, would the equilibrium and the reaction stay the same?
If I change the concentrations of all of them by the same factor, nothing would change. Like if I doubled the concentration of both reactants and the product, it's not going to affect it.
What is it if you add so much that if you have excess of nitrogen or any one of those?
Well, if you had a situation like in an aqueous solution where you exceeded the solubility, then you'd have some problems. But this is a gas, and so
That wouldn't speed it up to some type of degree, just because there's more particles, more collision.
it'll speed up the forward reaction and the reverse
Yeah.
reaction.
Like the overall speed of the reaction.
It'll-
forward and reverse.
Yeah, if the concentrations are higher, the forward reaction will be faster and the reverse reaction will be faster. But the equilibrium position
Yeah, it
will
would
be
stay
the same.
Yeah.
Okay, so let's keep going. Let's talk about what happens if we change a volume. So here we have a system. Let's see if there's any more words on there. No. Okay. Here we have a system with carbon dioxide and calcium carbonate and calcium oxide. And we have, this guy is in the gas state. So gases are sensitive to temperature and volume changes. If we decrease the volume, then we're in effect increasing the concentration of that gas because we're squishing it together. Le Chatelier's principle said the equilibrium will shift to compensate. And so it will shift away from the carbon dioxide. It would be really great if they had the reaction on there.
Here's the next slide.
It's not on the next slide. So, yeah, this one's better to talk about because this is that same one that we've been talking about. So this is the 3H2 plus the N2 in equilibrium with the 2NH3. So all of these are in the gas state, and that's important. The change in volume affects the gases. So I've got it at equilibrium, and that's this illustration A. And now I'm going to squish it. I'm going to squeeze it. I'm going to decrease the volume. Well, that increases the pressure. You can think of it as increasing the concentration because you have more moles of gas in a smaller volume. So it wants to oppose that. Remember that the volume of gas particles depends on the number of particles, not on what they are. So we need to look at this reaction, and we're going to draw a line down the middle. We're going to look at the left and the right. How many moles of gas particles are on the reactant side? 4. So we have 4 moles of gas on the left. We've got 3 moles of hydrogen and 1 mole of nitrogen. On the right side, we have 2 moles of gas. Do you see that? So we're decreasing the volume, which increases the pressure. Le Chatelier's principle says the equilibrium wants to shift to oppose that. It wants to reduce the pressure. How can it reduce the pressure? By reducing the number of gas particles. So if the reaction proceeds in the forward direction, we can cut the number of gas particles in half. So, these are hard to make up numbers
So
for.
it turns into a liquid?
No, it doesn't turn into a... Well, if you squished it far enough, it would. But that's not what we're doing here. The predicting a shift based on volume for gases we do by looking at the number of particles on each side. So on the left there were 4 particles, on the right there's 2. So if the equilibrium shifts to the right, we'll end up with fewer particles. That will reduce the pressure, right? That reduces the pressure and helps to counteract what we did to it. We put pressure on it by changing the volume, making the volume smaller. Smaller volume, higher pressure. The system wants to fight back. It wants to reduce the pressure. It can do that by shifting so that there are fewer particles. Not happening for you?
Where do they go?
Where do they go? Okay, that's a good question. Well, 3 hydrogen molecules and 1 nitrogen molecule combine to form 2 ammonia molecules. And yes, the mass is the same. but this is a gas. The ammonia particles are bigger than the nitrogen or the hydrogen particles. But that doesn't matter because there's so much empty space. It's the number of particles. Gas pressure depends on the number of particles. It's weird, I know. What happens if we increase the volume? Increasing the volume decreases the pressure. It's going to shift the other way to increase the pressure. The volume of the container, if we make the volume bigger, the pressure goes down. So, let's see if we can bring that. Yes.
Different than for an adult, when a baby has that much.
It's a lot, yes.
So as they get bigger, they can handle it better, because it's not the same.
Yeah.
What?
We're talking about colic, yeah.
And they know what's
Humans
going
do
on.
that?
Humans get colic, yeah.
Yeah, babies.
They just don't explode from
That's
it.
why I start paying attention more
They
to my own body
toot.
than
They
some
toot,
other
and the babies scream and cry because it's uncomfortable. So let's think of this equation again, and what if we're increasing the volume? We make the container bigger. Then now the pressure has gone down, and you might think, well, it's going to like that. Well, no, it just doesn't like change, period. No matter what the change is, it fights back against the change. So if you reduce the pressure, the equilibrium will shift to increase the pressure again. Well, then it's going to shift to the left and make more particles. And so you can actually cause this reaction to go back and forth depending on, by just, compressing and decompressing it.
You can do it with temperature too, right?
You can do it with temperature too.
So it may actually, so back to the pressure thing, when you increase pressure, so there's still, so because there's 2 moles compared to 4 moles, there's actually less number of particles.
Right, on the product side.
So that, okay.
So it'll go to that side. It's like, well, okay, if
Well,
I
I had to remember what moles mean. I was trying to figure out what you meant by less number of particles, because there would still be the same number of individual.
there's still the same number of atoms.
Yeah, atoms, but the
But they're
molecule now
combined
is less.
together.
Okay.
It's a little bit like, I guess, getting a group discount. You got a bunch of people going to, I don't know, some place that gives group discounts.
Okay.
And if you come in together as a group, if you have a group, it's per group. And so, hey, let's make more group, let's group up so that we don't have to pay so much to get in. Okay, I've got it. Grant Grove. You go to the national park, you pay per car to go in. So you got 10 people going up. Are they each going to drive their own car? No, because then you have to pay 10 times. It's like, okay, let's put 7 of them in the minivan and the other 3 in the Fit and take them up, and then we just have to pay twice. So it says, oh, there's a benefit to having fewer particles. We can reduce the pressure. So let's group up so that we can reduce the pressure. Is that better?
Yeah.
Okay, that was a good one.
Now I get it. Well, you were saying particles, and I was like, the same amount of stuff is still
Same number
there.
of atoms,
Of
but
atoms
gas
is still there.
molecules are different. Yeah. Okay, so change in temperature can also affect the equilibrium. And this is going to happen when we have exothermic or endothermic reactions. And so if we have an exothermic reaction, we can think of that as producing heat, right? An exothermic reaction gives off heat. Heat is a product. So if we add energy, if we add heat, we're adding a product, and the equilibrium shifts away from that. An endothermic reaction is the opposite. It absorbs energy, so heat is a reactant, and adding energy will shift the equilibrium to the right. We need an equation here. We just really, really do. So let's say that A plus B plus heat, this is an endothermic reaction, is in equilibrium with AB. So what we're going to do is we're going to treat heat like a reactant or a product. An endothermic reaction, you have to put heat in. You have to add it in. It's a reactant. In an exothermic reaction, it produces heat. Heat's the product. So if I increase the heat, if I add heat by changing the temperature, raising the temperature, if I increase the heat, the reaction wants to switch it, or shift to reduce that. So which way is it going to move? It's going to move away from that, right? It's going to shift to the right. I'll get more product at a higher temperature for an endothermic reaction. Does that make sense? If I cool it down, if I take heat away, it'll shift to the left, and I'll get less product. An exothermic reaction is the opposite. Put that in here. A plus B goes to AB plus heat. So here, if I add heat, it's going to cause it to shift to the left. So I'm adding heat, it's going to move to the left to get away, to undo what I did. If I decrease the temperature, then it'll shift to the right.
Do that again. The first one you did was the exothermic?
The one at the bottom is the endothermic.
And, it absorbed heat.
Mm-hmm.
So you took it away. And
Did you mean to put that second one underneath endothermic?
Pardon me?
Did you mean to put that second one underneath endothermic?
No, I didn't.
Okay, that's what.
And I'm zoomed in and I can't see
Okay, there we go.
the whole picture. So yeah, I'll just move that because that wasn't good. And we'll try to keep it the same colors too.
okay, so the first one you have absorbed heat. So you cooled it. Right?
No, the arrow up means increasing heat. I've increased the temperature.
So that's is that the exothermic?
That's it.
No.
Increase the heat, okay.
That's just changing the temperature, changing the conditions. Whether it's exothermic or endothermic is what side is the heat in the equation. So an endothermic reaction, you have to add heat. You have to put heat in, so it's a reactant. In the exothermic, it produces heat. Heat is a product. So in this exothermic one, if I increase the temperature, the equilibrium is going to shift away from that. And it'll shift to the left. It'll favor the reactants. So these concepts are used in manufacturing and in industry to make the chemical reaction do what you want. You know, if it's an exothermic reaction and you want to have it go forward, then you cool it. You suck that heat away and it'll keep shifting to try to replace that. And you can get the reaction to go more to completion. Is there anything left here? Okay, hopefully this will be good. So let's look at this reaction. Carbon dioxide decomposing into carbon monoxide and oxygen. It's in equilibrium, it's all gases. How many of these changes would lead to a shift in the equilibrium position towards the reactant? So it's asking us which of these will cause it to shift that way, to the left, to the reactants. So if I remove carbon dioxide gas, if I take some of this away, what's it going to do? It's going to try to replace that, right? So it'll shift this way. So that's not what it's asking. What if I add O2? It's going to react in a way to reduce that. So it's going to go this way to reduce that. So this is one of them. What if I remove CO2? I take CO2 away. It's going to go this way to replace that. What if I increase the pressure by decreasing the volume? Well, on this side we have 3 moles of gas. And on the left side, we have 2 moles. If I'm increasing the pressure, it wants to shift in a way to reduce the pressure. So it wants to go to the side with fewer molecules. So that'll make it go to the left as well. Increasing the pressure. If you increase the pressure, it will shift to the side with fewer gas molecules. If you decrease the pressure, it'll shift to the side with more gas molecules. And I hope this is the last one.
Why did it only circle 3?
Hmm?
It only circled 3.
Why only circle 3? Yeah, it was the number, how many of the changes, not which ones. Weird question. Yeah.
So if you decrease
We're going
the
to call that
pressure
done.
in the reaction.